Hey folks, I hope you're all doing well. This is a short video that will pick up in the middle of section 3.1. So in the previous video, we introduced polynomials and power functions and talked a little bit about their graphs and end behavior, and some terminology. So check out that video for that information. We will pick up and just talk about one more notion regarding polynomials, do a couple examples, and then go on to focus on quadratics, which is section 3.2 in the book. So polynomial intercepts. The graph of a function has two kinds of intercepts, a y-intercept and x-intercepts. The y-intercept is by far the simpler of the two. The y-intercept of any function, whether it's a polynomial or anything else, is just the function value at 0. This is because the y-intercept is on the y-axis and the x value on the y-axis is 0, so we just plug in an x or input value of 0. A function can only have one y-intercept because it has to pass a vertical line test. So it can't sort of go through the y-axis more than once. It might not have any y-intercept, but it can't have more than one. So this makes y-intercepts pretty straightforward. And so if we have a polynomial, here's a polynomial, or any other function for that matter, we get the y-intercept by just evaluating the function at 0. So when I plug in x equals 0, right? So this is my input-output rule. The input slot is where all the x's are. I just put zeros there and compute, and here I come out with 0. So the y-intercept here is 0. More precisely, the y-intercept is the point 0, 0. So let's just add that here. Point 0, 0. I mean, if you're talking about a y-intercept, then kind of automatically the x value is 0, but it's a little more precise to give both coordinates of the point. Here's another polynomial, right? So if I want to find its y-intercept, again, I just evaluate the function at 0. This is true for any function, whether it's a polynomial or not. So here's my input slot where the x's are. I put zeros there, and I do the computation. I come out with -8. And so the y-intercept is the point 0, -8. Okay, and that's that for y-intercepts. X-intercepts are a little more complicated. For one thing, a function can have more than one x-intercept, or it can have no x-intercepts. So you could have 0 x-intercepts, or 1 or 2 or 3 or 18 or any number. It's hard to tell. They are solutions to the equation f of x equals 0 because x-intercepts live on the x-axis, and the y value, or the output value along the x-axis, is 0. So we set the output equal to 0, not the input. This equation in general can be difficult to solve. It depends on the nature of f of x. And for most polynomials, this equation is too difficult to solve without the assistance of a computer. There are a couple of exceptions. If f of x is a linear function, we already know how to solve that equation from what we talked about before. Also, if the polynomial is in what's called factored form, and here is an example of a polynomial in factored form. Factored form means the polynomial is expressed as a product of a bunch of linear functions. So linear, that, like the blue highlighted thing, is a linear function. That's a linear function. That's a linear function. When you multiply them all together, you don't get a linear function, but the individual factors are linear functions. So if the polynomial is in this form, then the equation f of x equals 0 becomes not too hard to solve, right? So I have this equation. And the reason this is not too hard to solve is the left-hand side is a product, and a product is 0 only if one of the factors is 0, right? If you multiply two things and get 0, one of the things you're multiplying must be 0. That's the only way that can happen. So this just allows us to kind of separate this into kind of three different equations. Either the first factor is 0, or the second factor is 0, or the third factor is 0. And each of those equations is going to be a linear equation because the factors are linear. And so we can solve those easily enough. We just add 2, add 5, and subtract 3 respectively, and we get the solutions 2, 5, and -3. So this polynomial here in factored form has 3 x-intercepts, or roots is another term for these. And so that's worth mentioning here, a little bit more terminology. Okay, in terms of how to get a polynomial into factored form, don't worry about that. You should be able to go from factored form back to this kind of form just by kind of foiling out all the factors. That's just a piece from algebra. All right, let's quickly look at a couple of examples and then we'll talk about quadratics. So let's see, in 3.2, here I'm given this polynomial, and I just want to be able to quickly identify some things about it, right? So what is the leading term? This is review from the previous video. Remember, the leading term is the term with the highest power of x. It's not the term that comes first. So the leading term here is this term, minus 5x to the fourth, since that's the highest power of x. And the degree is the highest power of x, right? The term is the whole thing. The degree is just the power. So the degree here is just 4. Can I highlight the 4? Yeah, sort of. Okay, what about the end behavior of this polynomial? Well, when we're talking about end behavior, we focus on the leading term, the minus 5x to the fourth. As x goes to infinity, so as the input goes to the right, I know that x to the fourth goes up because the even powers are U-shaped, but the minus coefficient is going to reverse that and make it go down. So the answer to C is that the outputs will go to negative infinity. And the answer to D is exactly the same, right? Because x to the fourth goes up in both directions, to the left and to the right, and the negative coefficient will reverse both of those. And those, I believe, are the answers that we have here in the notes. So these will be preserved in the notes. They're in the exercise solutions, of course, on the Canvas page as well. Okay, what about this next example? So here I have another polynomial in factored form, and I want to find the intercepts, right? The y-intercept and the x-intercepts. Well, we know the procedure now. To get the y-intercept, I just evaluate the function at 0. And so that's going to look like this bottom line here, right? I take q of 0. You can see the input slot is right here, right? There's an x, there's an x, there's an x. So I just put a 0 into those spots. That's what this is right here. And then I just do some arithmetic and computing. And when the dust settles, I get 56, right? So the best way to report this, I think, is the y-intercept is the point 0, 56. And then the x-intercepts, and I did this quickly, but again, I just set each of the factors equal to 0. Now you might say, well, what about the 2 out front? That's a little different from our previous example. That doesn't really affect anything, because if you really go by the book and say, well, I have to set each factor equal to 0, that means that, let's see, 2 equals 0, or x minus 7 equals 0, or x plus 4 equals 0, or x minus 1 equals 0. But of course, this never happens. 2 is not equal to 0, so I don't get any solutions from the first equation. I only get solutions from these other 3 equations, right? And the solutions are 7, -4, and +1. Okay, so that's that, just kind of tying up some loose ends on polynomials. We are now going to focus on a specific kind of polynomial, in particular, a degree 2 polynomial. And that's what a quadratic function is. It's a degree 2 polynomial. So that means the highest power of x is 2. So looking back at our examples here, this is not a quadratic, it's degree 4. And if you multiplied this out, you would see that it's not quadratic either. Do we have any quadratics here? I guess we don't on this page. Okay, no matter. The most basic quadratic function of all is one of your toolkit functions, f of x equals x squared. So you're already familiar with this quadratic. It has this graph, this U-shaped graph. Here's an input-output table for it at the bottom. And there shouldn't be any surprises here, right? These are the inputs. The outputs are the squares, right? So square of 1 is 1, square of 2 is 4, square of 3 is 9, and so forth. And notice that the outputs are symmetric, right? Because when you square a negative number, you get a positive number. So -3 squared is the same as 3 squared. So it's not a one-to-one function, right? Clearly fails a horizontal line test, but it is a function. Okay, so let's see, that's the most basic kind of quadratic. Let's start to expand our scope a little bit. It turns out that all quadratic functions are transformations of this one. Now, we know they're polynomials of degree 2, that's the definition. It turns out that they're all transformations of this one, and that's kind of useful because we know something about transformations. So I think we have an example coming up soon. Well, before we get there, that means that all quadratics are going to have a graph that's similar in shape to this, right? If you take this graph and you shift it left or right, or you reflect it over either axis, or you stretch it somehow, you're still basically going to have a U shape. It's possible the U could be upside down, right? If you reflect it through the x-axis, then the U is going to flip over. But if we allow that, then all quadratics have this basic shape. It's called a parabola, so that's a sort of technical term for this kind of graph. And it has one sort of special point, and that's the point where the U changes direction, where my arrow is right now. So that's either the bottom or the top of the U, depending on what parabola you're talking about. And that point's called the vertex. So the vertex of this basic parabola, y equals x squared, is just the origin, the point 0, 0. Okay, let's see what happens here. Oh, so I think this is just a picture, right? Yeah, so that's just a picture up above. The purple point is the vertex. Okay, if a parabola is in a special form, it's easy to see the vertex. And here's an example of that special form, and we'll look at this in general in a moment. But take this specific example. If you multiply this out and do some algebra, you will see that this is a degree 2 polynomial. But notice that it's clearly a transformation of y equals x squared, right? What transformations do I do? Well, right here, I shift to the right by 1. And then when I multiply by 2, I stretch vertically. And then when I add 3 outside the function, I shift up by 3 units. So the vertex is not going to be affected by the stretch. The rest of the graph will, but it will be by the shifts. So if I take the origin and I shift it 1 unit to the right and 3 units up, I move it to the point 1, 3, right? So in this form, I can kind of see where the vertex moves. And I can see based on the transformations, there's no reflections here, so it's still going to be an upward opening U. So the graph here, I can just kind of spot by eye. I just take my blue curve, I shift over 1 and up 3. Now notice the scale on the axes is different. So it looks like I went further to the right than up, but that's only because of the different scale. And the orange U is a little more, a little steeper, right? It's been stretched vertically from the blue curve. Another example is this one, right? So here, what's the transformation? Well, I add 1 inside the function, so that goes left by 1 unit. Then I put a minus sign in front of it, so that reflects through the x-axis, and then I go down 5 units. Again, the only thing that affects the vertex is the shifting. So the origin goes left 1 and down 5, which means the new vertex will be the point -1, -5, right? Left 1, down 5, starting from the point 0, 0. So here is a picture. Right, the blue curve is my basic one, y equals x squared. I go left 1, down 5. Again, the scale on the axes is different here, so be a little aware of that. And then the reflection causes the U to flip over and be kind of upside down, right? I've used the x-axis as sort of a mirror. All right, so there's a couple examples of some transformations. In general, this form that this one is written in, and also this, is called vertex form for a parabola. And the general, is this the one I want to open? Yes, this is what that looks like in general, right? You can see in both of these, I've got some number out front here, and then I have x plus or minus something squared, and then I have another number added on the outside. So here is sort of a generic way to do that. And I can see the shifts here, right? So I shift by h horizontally and by k vertically, right? So in the example, this is a little different from the one up above, but here the a value is 2, that's the stretching factor. The h value is 4, that's the horizontal shift of the vertex, and the k value is 3, that's the vertical shift of the vertex. And it's called vertex form because you can kind of read the vertex right off of it, right? The vertex here is just h comma k, because the origin shifts by h horizontally and k vertically. Indeed, so it's easy to see two things from this form. First of all, as I say, the shift of the vertex from 0, 0 to hk. So this example here will have vertex 4, 3. And the other thing that is relatively straightforward to see from this form is which way the U opens, right? Because I start with a U, my original is an upward U, right? It opens up, and we'll call this kind of U concave up. And if the U opens down, like this orange curve here, we'll call that concave down. Well, the only way you can get from this curve to a concave down one is if you've introduced a minus sign, that is, if you've done this kind of reflection as one of your transformations. And if that happens, then this number out front is going to be negative. So if that number is negative, then the parabola is called concave down, right? The U faces down. And if it's positive, then there hasn't been a reflection, and so it is concave up, right? So here are a couple of examples in vertex form. And so after a little bit of practice, hopefully you will look at this and immediately see, okay, that's concave down because that's a negative number out front. And the vertex here is going to be at the point -7, 6. Be careful. Vertex form here is x minus h in parentheses. So x plus 7 is x minus -7, right? So a little careful with the sign on h, right? The h value here is -7, not +7. So the vertex is -7, 6. And as we said, the concavity here is this is concave down because of the negative. Here again, in this example, concavity is easy to see. This is also going to be concave down. The h value here will be -3. The k value will be +9. And so the vertex will be -3, +9, right? So those are just identifying the values. Vertex is -3, +9, and the concavity is concave down. Right. So notice that from vertex form, we can sketch a rough graph of the parabola without, any technology or really doing much, just by recognizing things in the form of the equation. Okay, another form that's a little more common than vertex form is called standard form. If we start with something in vertex form like this is one of the examples that we looked at up above. We can do some algebra here to re-express this, right? If I, for example, expand that square. So recall from algebra, the way you square a binomial is it's square the first plus twice the product of the two terms plus the square of the second. So the first is x, and the square of the first is x squared. That's where that first term comes from. The product of the two terms is x times -4, which is -4x, and twice that is -8x. That's where that comes from. And then the square of the second, -4 squared is +16. That's where the +16 comes from. And then once I'm done squaring, I can multiply the two through the parentheses and then combine some like terms, right? So you multiply through the parentheses, you hit every term, I get 2x squared minus 16x, and then plus 32. And then finally, I have two like terms here, 32 and 3. So I can combine those into 35. This form at the bottom here is called standard form, right? So given vertex form, we can easily put it in standard form just by doing a little bit of algebra. Indeed, this is the algebra in the standard form. Let's give the generic version of standard form. I think that's what this is. Looks like this, right? So this is what a degree 2 polynomial looks like, right? A degree 2 polynomial, but the highest power of x is 2, which means the only other terms you could have are an x to the 1 and an x to the 0, right? That's the constant term. If it's going to be a polynomial and it's going to be degree 2, nothing else is allowed. So I have three coefficients, which we'll usually call a, b, and c in order, right? So a is the coefficient of the x squared. And notice that the a is the same in vertex form and standard form. The advantage of this is that even if we started with it in standard form, I can recognize from that blue expression that this is a concave up parabola because the a is positive. All right, let's see what else here. So here's another example that we can work through. So here I am in standard, in vertex form rather. I think this is one from, yeah, that's one we looked at quickly up above. So if I square the binomial first, right, square the first is x squared, twice the product of the two is 6x, square the second is 9. Multiply the -8 through the parentheses, and I get that, right, -8 times x squared, and negative 8 times 6x is negative 48x, negative 8 times 9 is negative 72. And then combine the two like terms, the negative 72 and the 9, and I wind up with this in standard form. So there are my a, b, and c values. Notice that if there are negative signs, they get incorporated into the coefficients here, right? So in this example, all of the coefficients are negative. This is a concave down parabola, right? Because the a value is negative. As far as the vertex goes, right? So in vertex form, we could detect both concavity and the vertex. In standard form, it's a little more work to identify the vertex, but it turns out the x-coordinate of the vertex is x equals negative b over 2a. This takes a little bit of algebraic shenanigans to show, so we'll just accept this, but you can by all means investigate that on your own if you're interested. So for example, here is a parabola or a quadratic in standard form. And if I want to find the vertex, what do? Well, hopefully that's what we do here. The x-coordinate, so first, before we get to this, let's identify the coefficients, right? A equals 2, b equals negative 16, c equals 35. All right, so to get the x-coordinate of the vertex, I just use this formula, negative b over 2a. So that's negative 16, right? That's the negative b, and then 2a is 2 times 2. So that comes out to be 16 over 4, which is 4. This is the x-coordinate of the vertex. How do you get the y-coordinate? Well, if you know the x-coordinate on any function, you can find the y-coordinate. Just use the input-output rule, right? This is an input value. So put it in the input slot to determine what the output is. So when I do that, this is right here, right? You can see I put a 4 in the input slot, and then I just do some math, and it comes out to be 3. Right. So my conclusion here, let's add a conclusion, is that the vertex is the point 4, 3. All right. Another example, and then we'll talk about intercepts, and then I think that's about all we need for quadratics. So here's my quadratic. The x-coordinate of the vertex here, so b is negative 48, right? So negative b is positive 48. A is negative 8, so 2 times a is negative 16, and 48 over negative 16 comes out to be negative 3. And then to get the y-coordinate, I just put that into I compute the function value at x equals negative 3, right? So I put negative 3 into the input slot. Excuse me, that's done right there. And then I'll leave you to do the math there, and you come out with 9. So the vertex here is negative 3, 9. Okay, what about these? So now in either form, standard or vertex form, we can figure out concavity and the vertex. What about the intercepts of a quadratic function, right? So again, the y-intercept of any function is straightforward. It doesn't matter whether it's quadratic or not. It's just the function value at 0. So if my quadratic is, there's a sort of generic quadratic, ax squared plus bx plus c, here's the input slot. If you put a 0 in for x, the first two terms just disappear and you're just left with c, right? So in this specific case, you can kind of see the y-intercept. It's just the constant term. So for example, for this one, the y-intercept is the point 0, 35, right? There's the constant term. For this one, the y-intercept is 0, negative 63. Y-intercepts are not that difficult. Okay. If the quadratic is in factored form, we saw this for polynomials in general a moment ago, so it works for quadratics as well. If it's a quadratic and it's in factored form, it will have only 2 factors. And from factored form, it's easy to see the x-intercepts, right? The roots, this is a repeat of what we said before. So for a quadratic in factored form, like the one here, the roots are going to be 9 and 2, right? X equals 9 and x equals 2. Okay, indeed. So that's just what I just said. If a quadratic is in standard form, how do you find the x-intercepts, right? So what if you have something like this or something like this? How do you find the intercepts? Well, you can factor it, and many of you have in algebra have worked on factoring quadratics, and so you know how to come up with this kind of form, and that's fine. That works perfectly well. But something that always works is the quadratic formula, which is given by this. This is a formula for the x-intercepts of a quadratic. The a, b, and c are the coefficients from standard form. Since this is a remote course, there's no issue of memorizing the quadratic formula. You can always look it up and be sure that you have the right formula to use. So here's an example. F of x equals negative 3x squared minus 5x plus 2. The y-intercept is 0, 2, right? The y-intercept's the easy one. That's just given by the constant term. Let's see what we do next here. It's concave down because the leading coefficient is negative, right? The a value is negative. So there's a number of things that we can recognize right off the bat. As far as end behavior goes, well, for quadratics, this is simpler to analyze because they're all U-shaped, right? So it's either an upward opening U, concave up, or a downward opening U, concave down. This one is downward opening. And if it's downward opening, it means that the function goes to negative infinity in both directions. If it's upward opening, then it goes to positive infinity in both directions, right? So again, all of this we can just kind of recognize right from the form of the quadratic. All right, what about the vertex of something like this? Well, here I have to recognize, all right, this is in standard form, so I'm going to use the minus b over 2a expression to get the vertex. My coefficients are negative 3, negative 5, and 2 respectively. So the x-coordinate of the vertex will be minus b is minus negative 5, right? That's the numerator. And then 2 times a is 2 times negative 3. And if I do some math here, I come out with negative 5, 6, which is about minus 0.83. And to get the y-coordinate, well, if you know the input value, just use the rule to get the output value. So I'm just going to compute f of negative 5, 6. Right, that is, I put negative 5, 6 in the input slot for this function, and that looks like this. And if I load that into a calculator, I come out with 4.08. Okay, so the vertex here is the point. Hopefully that's the next thing we say. Yes, the vertex is the point negative 0.83, comma 4.08. Notice that vertices and roots don't have to come out to be nice round numbers. They might be a little bit messy, but that's okay. One number is just as good as another. What about the roots? Remember, roots are x-intercepts, right? So what I'm asking here for are the x-intercepts. Well, it's in standard form, so we'll have to use a quadratic formula to find the roots. So that's just a copy of the quadratic formula from up above. When I load my coefficient values in, remember these are the coefficient values right here. And so I'm just identifying them again, going slowly. All right, now let's load them into the quadratic formula. It looks like this, right? You can see there's the b, negative 5, and then there's the b squared, right? 4, a is negative 3, c is 2, 2 times a is negative 3. And then there's a lot of sort of computing and arithmetic to do. And when you do some simplifying here, you wind up with this expression over on the right. The one thing about the quadratic formula that takes a little getting used to is this plus or minus that's kind of embedded in the numerator. And the result of that is very often this answer is not one answer, but two, one if you choose plus and one if you choose minus, right? So here, if I choose plus in the numerator, I get 5 plus 7 over negative 6, which comes out to negative 2. And if I choose minus, I get 5 minus 7 over negative 6, which comes out to 1/3. So I have two x-intercepts here. Remember we said above, functions can have more than one x-intercept. So there's nothing sort of wrong with this. We'll only get one y-intercept, but we could get many x-intercepts. So for a quadratic, it either has 0, 1, or 2 x-intercepts. It turns out that polynomials can't have more x-intercepts than their degree, right? So a degree 4 polynomial can't have more than 4 roots. A degree 2 polynomial, that's a quadratic, can't have more than 2 roots. Well, if you can't have more than 2, then you're going to have 0, 1, or 2, right? Those are your only options. And which is the case will just kind of fall out of the quadratic formula. What happens is if this thing under the square root is a positive number, then you're going to get two roots, just as we did in this example. If it's a negative number, then this doesn't make any sense. You can't take the square root of a negative number. And the conclusion will be that that quadratic doesn't have any roots. And if it turns out to be equal to 0, well, then this whole piece just goes away and you only get one root. So this isn't something that we have to kind of look at the original function and figure out. It will just fall out of applying the quadratic formula. All right, let's quickly look at this other example and then wrap this, this particular video up. So here I have a quadratic. This is in vertex form, notice. So let's see, what's the first thing we want to recognize about this? Let's find the x-intercepts for this, starting from vertex form. There is more than one way to do this. What I am going to do, I think, is go ahead and put it in standard form and use the quadratic formula again. Okay, so I square the binomial, right? Square the first is x squared, twice the product of the two terms is 2 times x, and square the last is 1 squared, which is 1. And then I distribute the minus sign through the parentheses, and I combine the two like terms at the end, the -1 and the -5, to give me this thing at the end. Okay, so then to find the vertex, I will use the quadratic formula. Right there are my coefficients, -1, -2, -6. When I plug into the quadratic formula, and I'm going a little quickly here, but you can always pause the video and slow things down if you want while you're watching. But this is really just plugging into a formula, right? So the b value is -2, so minus b out front here becomes +2. And then b squared is 4, there's 4, a is -1, c is -6, etc. And in this example, we see that what happens is you wind up with a negative number under the square root. So this doesn't make any sense. We can't take the square root of a negative number. And so our conclusion here is that there are no x-intercepts. And again, this can happen. This is a viable answer to the question of what are the x-intercepts of this quadratic. I would note, and we don't do this here in this example, but other things we can tell quickly from this is a concave down parabola because of that minus sign. And the vertex here is going to be -1, +5 because it's in vertex form. It's easy to read off the vertex. Okay, so there are, of course, a number of other exercises in the notes and exercises in the book. I urge you to practice. You can check all your solutions. If you have questions, send me an email, and I will open all these solutions in the notes that I post on Canvas. Take good care of yourselves, folks.